Popular culture has trained you to picture this moment incorrectly. The comic book version looks almost gentle. A spider bites, there is a flash of discomfort, maybe a fever dream of a night. And by morning, the person can climb walls and see danger before it happens. Almost none of that is accurate. A radioactive bite is not a superpower delivery system. It is a massive, targeted dose of ionizing radiation delivered directly into the bloodstream. And the actual biology of what happens next is far stranger and far more lethal than anything a comic book has ever shown you. Let's go through it properly. Radiation damage has two components that need to be understood separately. The first is the dose. How much energy is actually absorbed by tissue, measured in a unit called the sievert. The second is what that energy actually does once inside the body, which is not activate anything, it breaks things. Ionizing radiation strips electrons from molecules, and when those molecules happen to be strands of DNA inside a living cell, the result is a break, a mutation, or outright cell death. You need a very specific, narrow, almost impossible combination of factors for a radiation exposure to change a cell's function without simply destroying it. A spider bite delivering that dose doesn't get to choose which outcome it produces. Biology doesn't work that precisely, and it never has. This is why the two most common outcomes of a hypothetical radioactive bite are mechanically so different from what fiction portrays. The first is localized tissue destruction. The venom itself, real spider venom, already causes localized cell death in a bite wound. Layer a radioactive dose from an irradiated spider's fangs on top of that, and you get accelerated severe necrosis at the bite site, not proliferation. The second outcome, if the dose is somehow survivable and diffuse, is systemic radiation sickness, nausea, immune collapse, bone marrow suppression. The same syndrome documented in every real human case of significant radiation exposure. Two very different injuries, and neither one converges on Spider-Man. So what would a bite like this actually look like from the outside? Not like the movies. The immediate wound would show the same puncture pattern as any spider bite: redness, localized swelling, but the surrounding tissue would begin breaking down faster and more severely than venom alone explains. There would be no shimmering veins, no dramatic muscle definition appearing overnight. Within hours, if the dose were significant, the first signs of acute radiation exposure would begin: nausea, vomiting, fatigue. Doctors quantify radiation exposure using absorbed dose thresholds established from real historical data: atomic bomb survivors, nuclear accident victims, radiation therapy patients. And a dose concentrated enough to meaningfully alter a person's DNA at the cellular level is, without exception, in every documented case, closer to a fatal dose than a transformative one. Now to the question almost everyone actually wants answered. Could you get even one power out of this? For the vast majority of exposure levels, the evidence-based answer is no, not in any way current biology allows. But this gets complicated in an interesting way, because radiation causing a beneficial mutation is not technically science fiction. It's a real, documented, if exceedingly rare phenomenon. This is where a genuinely strange body of research enters the picture. Radiation-induced mutations happen constantly, in nature and in labs, and the overwhelming majority are either neutral or harmful. But mutation is also the raw material of evolution itself, and there are documented cases, mostly in bacteria and simple organisms, of radiation exposure producing a mutation that turned out to be advantageous under specific conditions. In humans, the picture is far grimmer. Every well-studied human population exposed to significant radiation, the survivors of Hiroshima and Nagasaki, the Chernobyl liquidators, radiation accident victims worldwide, shows the same pattern: elevated cancer rates, developmental damage, no confirmed case of a beneficial trait emerging from the exposure. The dose required to meaningfully rewrite human genetic material in one localized event is, in essentially every documented scenario, high enough to kill the person carrying it. Follow-up research into targeted low-dose radiation has estimated that certain very specific medical techniques, like radiotherapy calibrated to damage only cancerous tissue, can achieve controlled, beneficial cellular change, but only through slow, repeated, carefully measured microdoses over weeks, monitored by machines that can control exposure down to the millisievert. This isn't evidence that a single spider bite could ever replicate that. It's evidence that the entire premise requires exactly the kind of control a spider fang cannot deliver. A real venomous bite, though, appears to be a genuinely separate story, worth understanding on its own terms, and the distinction matters. Spider venom is a cocktail of enzymes and neurotoxins evolved over millions of years, not to enhance the bitten creature, but to immobilize or begin digesting it. Studies of necrotic arachnid venom, the kind found in recluse spiders, have found that it actively breaks down cell membranes at the bite site, the exact opposite of the radiation hero fantasy. The bite that would give you focused, isolated superpowers and the bite that would put you in a hospital's burn unit turn out to be, biologically, almost the same category of event. That said, hearing about real venom research is not entirely disconnected from the superhero fantasy, which is part of why scientists studying venom take it so seriously as a field. Venom compounds, extracted carefully in labs, have led to real medical breakthroughs. Blood pressure medications derived from snake venom, pain research derived from scorpion and spider toxins. Given how much untapped pharmacological potential sits inside venom, and given how much modern medicine already owes to it, most researchers argue venom deserves more careful study, not comic book radiation. The path from spider bite to actual documented human enhancement also bears almost no resemblance to the fictional version. The real story of humans gaining unusual physical traits runs through a completely different door: rare genetic mutations, not radiation exposure, sometimes producing dramatically increased muscle mass through a myostatin deficiency, or exceptional bone density through mutations like LRP5. These are naturally occurring in a tiny number of documented human cases. No spider, no fangs, no bite required. Just an inherited quirk in a single gene passed down at conception. Outcome depends heavily on which door you're imagining walking through. A genetic mutation, inherited or occurring naturally, can, in extremely rare cases, produce a stable, functional physical difference across an entire lifetime. Radiation exposure, delivered suddenly and locally, almost never does. It correlates with worse outcomes, largely because concentrated ionizing radiation is simply not a precision instrument, not because the concept of dramatic biological change is itself impossible. There are well-documented cases of extraordinary human physical traits. None of them trace back to a bite. Which leaves the question this whole subject circles back to. If the honest biology of a radioactive spider bite points overwhelmingly toward necrosis, radiation sickness, and in the worst documented dose ranges, death, while the rare cases of real human enhancement trace back to inherited genetic mutations with no radiation and no spider involved at all, then the honest answer to what would really happen is not the story 80 years of comic books have told you. It's a story about how badly fiction misunderstood two of the most misunderstood tools in biology, radiation and venom, and got the ending backwards.